Hello everyone, my name is Madhuri Gupta, working as an assistant professor in the Department of Computer Science, Chhattisgarh Swami Vivekanand Technical University, Bhilai. Today our topic of discussion is alpha beta cutoff. Before that, let's have a quick recap on our last lecture on min-max search. The min-max algorithm, we have the introduction, the lecture introduction, the min-max search algorithm, a decision making strategy used in games and artificial intelligence. Game theory, it explained that min-max is commonly applied in two-player zero-sum games where one player's gain in the other's loss, such as chess, checkers or tic-tac-toe. The primary objective of the min-max search is to find the best move for the maximizing player while minimizing the potential loss, that means maximize gain for the minimizing player. Game tree, a game tree was introduced as a visual representation of possible moves and outcomes in a game. Each node represents a game state and branches represent possible moves. Depth of search, the lecture highlighted that the min-max algorithm explores different depths of the game tree, looking ahead to predict future outcomes. Deeper searches lead to better decision but require more computational power. The value assignments, it explained how the algorithms assigns values to each node, representing the desirability of that position for the maximizing player. Higher value are better and the minimizing player lower value are better. Backtracking, the lecture touched upon how the min-max algorithm backtracks through the game tree to select the best path considering the calculated value. And we have used pruning. It introduced the concept of alpha beta pruning, a technique to eliminate branches in the game tree that are guaranteed to be suboptimal. This pruning significantly reduced the search space, making the algorithm more efficient. And the applications are, the lecture mentioned that the min-max algorithm isn't limited to games, but has broader application in fields like artificial intelligence, economics and decision making. So, we have the conclusion of our last lecture. The lecture concluded by emphasizing the power of the min-max algorithm in strategic decision making and its significance in various domains. In summary, we can say that the lecture provided an overview of the min-max search algorithm, explaining its fundamental principles, how it navigates game trees and its broader application beyond games. Now, let us start with our today's topic, alpha beta pruning. Alpha beta pruning is a modified version of the min-max algorithm. It is an optimization technique for the min-max algorithm. As we have seen in the min-max search algorithm that the number of game states it has to examine are exponential in depth of tree. Since we cannot eliminate the exponent, but we can cut off it to half. Hence, there is a technique by which without checking each node of the game tree, we can compute the correct min-max decision, and this technique is called pruning. This involves two threshold parameter alpha and beta for future expansion. So, it is called alpha beta pruning. It is also called as alpha beta algorithm. Alpha beta pruning can be applied at any depth of a tree, and sometimes it is not only prune the tree leaves, but also entire subtree. The two parameter can be defined as alpha and beta. Alpha means the best highest value choice we have found so far at any point along the path of the maximizer. The initial value of alpha is minus infinity. Beta, the best lowest value choice we have found so far at any point along the path of minimizer. The initial value of beta is plus infinity. The alpha beta pruning to a standard min-max algorithm returns the same move as the standard algorithm does, but it removes all the nodes which are not really affecting the final decision, but making algorithm slow. Hence, by pruning these nodes, it makes the algorithm fast. Note: to better understand this topic, kindly study min-max algorithm before, then study this topic, then you will get the better understanding. So, here are some conditions for alpha beta pruning. The main condition which required for alpha beta pruning is: first, alpha should be greater than equal to beta. Key points about alpha beta pruning: first, the max player will only update the value of alpha. The min player will only update the value of beta. While backtracking of the tree, the node value will be passed to upper nodes instead of values of alpha and beta. We will only pass the alpha beta values to the child nodes. So, here are the pseudocode for alpha beta pruning. Step 1, function min max, which includes node, depth, alpha, beta, maximizing player. Second, if depth is equal to 0 or node is terminal node, then step 3, return static evaluation of node. If maximizing player, then for maximizer player, max evaluation is equal to minus infinity. For each child of node, do evaluation is equal to min max child depth minus 1 alpha beta false. Max evaluation is equal to max evaluation alpha is equal to max alpha max evaluation. If beta is less than equal to alpha, then break, return max evaluation. Else, for minimizer player, min evaluation is equal to plus infinity. For each child of node, do evaluation is equal to min max child depth minus 1 alpha beta true. Min evaluation is equal to min evaluation beta is equal to min beta evaluation. If beta is less than equal to alpha, break, return min evaluation. So, this is all about the pseudocode. So, now let us have the working of alpha beta pruning. Let us take an example of two player search tree to understand the working of alpha beta pruning. Step 1. At the first step, the max player will start first move from node A, where alpha is equal to minus infinity and beta is equal to plus infinity. This value of alpha and beta pass down to node B, where alpha again is equal to minus infinity and beta is equal to plus infinity, and node B passes the same value to its child D. So, let us start with the working of alpha beta pruning. Let us take an example of two player search tree to understand the working of alpha beta pruning. Step 1. At the first step, the max player will start first move from node A, where alpha is equal to minus infinity and beta is equal to plus infinity. These values of alpha and beta pass down to node B, where alpha is equal to minus infinity and beta is equal to plus infinity, and node B passes the same node to its child D. here in this, you can see in this diagram how we can distribute the value of alpha and beta. You can see in the parent node A, where we have alpha is equal to minus infinitive and beta is equal to plus infinitive, and you can see the diagram. Here we have parent node as max player, and then we have min player, then we have max player, and in the terminal we have value to the each node. So, you can see the value in the terminal node that we have D is equal to 2, 3, then E has the children 5 and 9, then we have F is equal to 0, 1 and G is 7, 5. So, we have to explore this value using alpha and beta cutoff. So, let us see in the step 2. At node D, the value of alpha will be calculated as its turn for max. The value of alpha is compared with firstly 2 and then 3, and the max 2, 3 is equal to 3, because max is equal to 3 will be the value of alpha at the node D, and node value will also 3. Step 3. Now, algorithm backtrack to node B, where the value of beta will change as this is a turn of minimizer. Now, beta is equal to plus infinitive. We will compare with the available subsequent nodes value, that is min alpha, that is min, infinitive and 3. We have to compare these two value. So, infinitive and 3 will get the 3, because hence at node B now alpha is equal to minus infinitive and beta is equal to 3. So, this changes you can see in this diagram. We have changed the value of D to 3. We have to compare alpha value. So, alpha is equal to 3 and beta is equal to minus infinitive, and this value is backtracked to the value of B, because B is playing as a minimizer. So, beta is equal to 3 and alpha is equal to minus infinitive. So, this is about step 2. Now, step 3. In the next step, algorithm traverses the next successor of node B, which in the next step algorithm traverses the next successor of node B, which is node E, and the value of alpha is equal to minus infinitive and beta is equal to 3 will also be passed. Step 4. At node E, max will take its turn and the value of alpha will change. The current value of alpha will be compared with 5. So, max minus infinitive 5 is equivalent to 5. Hence, at node E, alpha is equal to 5 and beta is equal to 3, where alpha is greater than equal to beta. So, the right successor of E will be pruned and algorithm will not traverse it, and the value at node E will be 5. So, you can see the changes in this diagram. So, you can see the changes. We have the value of you can see the value of B is now alpha is equal to minus infinitive, beta is equal to 3. Now, we have to move toward E. So, E is equal to 5. So, because 9 is cut, because 9 is already higher the value. So, we have to cut the 9 value. So, we have the value E is equal to 5 and this value is backtracked to the upper level. Step 5. At next step, algorithm again backtrack the tree from node B to node A. At node A, the value of alpha will be changed. The value available value is 3, as max is equal to minus infinitive and 3. So, we have 3 and beta is equal to plus infinitive. These two value now passes to right successors of A, which is node C. At node C, alpha is equal to 3 and beta is equal to plus infinitive, and the same value will be passed on the node F. Step 6, at node F, again the value of alpha will be compared with left child, which is 0, and max is equal to 3 0. So, we have 3, and then compare with right child, which is 1, and max is equal to 3 1. We have to compare 3 and 1. So, we will get the max value 3. Still alpha remains 3, but the node value of F will become 1. So, you can see this changes in the diagram. So, you can see the value of C is beta is equal to infinitive and alpha is equal to 3, and in the F value you can see the value of beta is equal to infinitive and alpha is equal to 3, and F value of F is equal to 1. So, now see the next step. In step 7, node F returns the node value 1 to node C. At C, alpha is equal to 3 and beta is equal to plus infinitive, hence the value of beta will be changed. It will compare with 1. So, mean value is infinitive 1. So, we get 1. Now, at C, alpha is equal to 3 and beta is equal to 1, and again it satisfied the condition alpha is greater than equal to beta. So, the next child of C, which is G, will be pruned and the algorithm will not compute the entire subtree. So, you can see this changes in this diagram. We have to prune the G subtree because it is not useful for our next search. So, we have pruned this G value 7 and 5 because it is not satisfied the alpha is greater than equal to beta condition. So, we have to prune this subtree. Step 8, C now returns the value of 1 to A. Here the best value of A is max 3 1. So, we get the 3. Following is the final game tree, which is the showing the nodes which are computed and nodes which has never computed. Hence, the optimal value for the maximizer is 3 for this example. You can see in this diagram we have the value defined. A is equal to 3. So, we have best value for A is equal to 3, and in the green line you can see the best path from A to B, B to D and D to this 3 value. So, this is the best path and the best value will be 3. So, move ordering in alpha beta pruning, how the move can be ordered. The effectiveness of alpha beta pruning is highly dependent on the order in which node is examined. Move order is an important aspect of alpha beta pruning. It can be of two types. Worst ordering. In some cases, alpha beta pruning algorithm does not prune any of the leaves of the tree and works exactly as min-max algorithm. In this case, it also consumes more time because of alpha beta factors. Such a move of pruning is called worst ordering. In this case, the best move occurs on the right side of the tree. The time complexity for such an order is order of b to the power m. Next is idle ordering. The idle ordering for alpha beta pruning occurs when lots of pruning happens in the tree and the best move occur at the left side of the tree. We apply depth first search, hence it first search left of the tree and go deep twice as min-max algorithm in the same amount of the time. Complexity in idle ordering is order of b to the power m by 2. So, now we have some rules to find good ordering. Following are some rules to find good ordering in alpha beta pruning. Occur the best move from the slowest node. Order the nodes in the tree such that the best nodes are checked first. use domain knowledge while finding the best move. For example, for chess, try order, captures first, then threats, then forward moves, backward moves. We can bookkeep the states as there is a possibility that a state may repeat. So, now let us have example 2 for our alpha beta cutoff. Let us walk through a simple example of alpha beta pruning technique to illustrate how alpha and beta values are used to evaluate nodes in a game tree. In this example, we will use a binary tree which represent a simplified game scenario where two players max and min take turns to make moves. Consider the following game tree. We have max, min, min, max, max, min, min. So, in terminal we have 3, 12, 8, 2 and 6 and 14 value. In this tree, max represent the maximizing player, min represent the minimizing player. The numbers at the leaf nodes represent the value of each game state. We will use alpha beta pruning to find the optimal moves for max. We start with alpha as negative infinitive and beta as positive infinitive. First, max node, value minus infinitive and plus infinitive. Max explores left child node. It sets alpha to 3, the value of the left child, and the continue exploring. Second, min node 1, value 3, infinitive. Min explore the left child node. It sets beta to 3, the value of the left child, and continues exploring. Step 3, max node 2, value 3 and infinitive. Max explore the left child node which has a value of 12. Since 12 is greater than 3, that means alpha, max updates alpha to 12 and continues exploring. Step 4, min node 2, value 3, 12. Min explore the left child node with a value of 8. Since 8 is less than 3 beta, so min prunes this branch and does not explore further. Min sets its value to 8. Now, in step 5, max node 3, value 12 and infinitive. Max explore the right child node which has a value of 8. Since 8 is less than 12, that means alpha, max prunes this branch and does not explore further. Max sets its value to 12. Min node 3, value is 12 and infinitive. Min explore the right child node which has a value of 6. Min updates beta to 6 and continues exploring. Now, in next step, max node 4, value 12 and 6. Max explore the left child node with a value of 2. Since 2 is less than 6, max prunes this branch and sets its value to 12. Now, in next step 8, min node 4, value 12 and 6. Min explore the right child node with a value of 14. Min updates beta to 14 and continues exploring. In step 9, max node 5, value 12 and 14, max explore the left child node with a value of 6. Since 6 is less than 12, that means alpha, max prune this branch and set its value to 12. Now, in step 10, min node 5, value 12 and 14, min explore the right child node with a value of 14. Since 14 is greater than 12, that means alpha, min sets its value to 14. At this point, We have explored all relevant branches and Max has determined that the optimal move is to choose the left child of the root node which correspond to a value of 12. So, in this example using alpha beta pruning, we have efficiently pruned away branches that did not affect the final decision, reducing the search space and finding the optimal move for Max. Alpha beta pruning is a powerful technique used in game tree and search algorithm, but like any method it has advantages and limitations. So, let us have advantages of alpha beta pruning. First, efficiency. Alpha beta pruning significantly reduces the number of nodes that need to be evaluated in a search tree. This makes it possible to search much deeper into the game tree within a limited amount of time, improving the quality of decisions. Second, time complexity. The time complexity of the alpha beta pruning is order of b to the power d by 2, where b is the branching factor, that means average number of children per node, and d is the depth of the tree. This is a significant improvement over the brute force search of order of b to the power d in most cases. Third, memory efficiency. Alpha beta pruning does not require storing the entire game tree in memory, which is especially advantageous for games with large state space. Fourth, guaranteed correctness. Alpha beta pruning is guaranteed to produce the correct result as long as the heuristic evaluation function is accurate. It will not miss the optimal moves. Fifth, widely applicable. Alpha beta pruning is not limited to specific games like chess. It can be applied to various games and search problems where there is an ordered search space. Now, limitation of alpha beta pruning. First, complete information. Alpha beta pruning assume that the entire game tree is known and can be explored. In games with incomplete or imperfect information such as card games like poker, it becomes less effective. Second, static evaluation function. It relies on a static evaluation function to estimate the value of game tree. If the evaluation function is inaccurate, alpha beta pruning may not always find the best move. Third, branching factor. Alpha beta pruning's effectiveness depends on the branching factor of the game tree. In games with a high branching factor such as chess, it can still be computationally intensive. Fourth, ordering of moves. The performance of alpha beta pruning depends on the order in which moves are considered. If the best move is near the end of the list, the pruning benefits may not be fully realized. Fifth, memory overhead. While it is more memory efficient than storing the entire game tree, alpha beta pruning still requires maintaining alpha and beta values for each node, which can become significant in deep searches. Parallelization challenges. Parallelizing alpha beta pruning can be challenging, especially in shared memory systems due to the need to update and synchronize alpha and beta values. Seventh, transposition tables. For games with repeated positions like chess, the algorithm can benefit from transposition table, which add complexity to the implementation. In summary, alpha beta pruning is a fundamental and highly effective technique for searching game tree, but it is not without limitation. Its efficiency relies on factors such as the accuracy of the evaluation function, the branching factor of the game, and the order in which moves are considered. While it is widely used in broad games and AI application, it may not be suitable for all type of search problems or game with incomplete informations. So, here we have the difference between alpha beta cutoff and min max search. Min max search and alpha beta pruning are two related techniques used in game playing algorithms, particularly in game with two player like chess. They have distinct roles within the same framework, and the primary differences between them is in how they search through the game tree and evaluate possible moves. Min max search. First basic idea, min max search is a decision making algorithm that aims to find the best moves for a player, assuming that the opponent will make the optimal move for their own advantages. Operation. It works by recursively exploring the game tree to evaluate the utility or the value of each possible game state. For each player's turn, it selects the moves that maximizes the player's utility. If it is the player's turn, that means maximizing player, or minimizes the utility if it is the opponent's turn, that means minimizing player. Third, optimality. Min max ensure that the player chooses the move that maximizes their chances of winning while considering the best possible response from the opponent. It guarantees the optimal moves if the game tree is completely explored. Now, alpha beta pruning. The basic idea, alpha beta pruning is an optimization technique applied within the min max framework. It reduces the number of nodes evaluated in the game tree search by eliminating branches that cannot affect the final decision. Second, operation. Alpha beta pruning maintain two values, alpha, that means the best value that the maximizing player can guaranteed, the beta, the best value that the minimizing player can guarantee. As it explores the game tree, it prunes branches where it is certain that they won't affect the final decision, especially if it finds a move that leads to a worse outcome for the player whose turn it is maximizing or minimizing. It stop evaluating that branch. Third, optimality. Alpha beta pruning does not compromise the optimality of the min max algorithm. It still ensures that the best move is chosen. However, it does so more efficiently by cutting off unnecessary branches. So, key differences. First, purpose. Min max focuses on finding the best move considering optimal play from both players, whereas alpha beta pruning on the other hand is an optimization technique applied within the min max framework to reduce computational effort. Efficiency. Alpha beta pruning significantly improves efficiency by eliminating parts of the search tree that cannot impact the final decision. Min max, when applied without pruning, explores the entire tree. Order of evaluation. Min max evaluates all nodes in the order presented by the game tree. Alpha beta pruning may evaluate nodes in a different order, but will still identify the optimal moves correctly. Fourth, guaranteed optimality. Both min max and alpha beta pruning guaranteed that the chosen move is optimal if the entire game tree is explored. However, alpha beta pruning reaches the same result more quickly by avoiding unnecessary exploration. In summary, min max search is the fundamental decision making algorithm for two player games while alpha beta pruning is a technique that improves the efficiency by reducing the number of nodes evaluated. They work together to find the optimal move efficiently while ensuring that the best responses to the opponent's move is considered. I am thrilled to introduce our upcoming lecture on the branch and bound algorithm. Branch and bound is a powerful technique used in optimization and search problem. From resource allocation to scheduling and beyond. In this lecture, we will delve into the fundamental of this algorithm, exploring how it transforms complex problem into manageable steps, ultimately providing optimal solution. We will begin by understanding the core concept of branching as a way of break down problem into smaller sub problems. We will then explore how bonding technique help us eliminate sub problems that are guaranteed to lead to suboptimal solutions, thereby significantly reducing the search space. Throughout the lecture, we will walk through the real world examples showcasing the versatility and practicality of the branch and bound in various domains. We will discuss its application in areas such as traveling salesman problem, job scheduling and more. By the end of this lecture, you will have a solid understanding of how branch and bound works and how it can be applied to tackle complex optimization challenges. So, be prepared to embark on a journey of problem solving and algorithm elegance as we explore the branch and bound algorithm in depth. See you there. So, thank you for watching and we will see you in the next lecture.